slowly flowing. They are not, strictly speaking, static reservoirs. They are slowly flowing, but the flow is very slow, and therefore we don't distinguish between storage and flow. For surface water, we distinguish between stored water, reservoirs, and flowing water, rivers. It is typically easier to assess surface water availability than groundwater, and the reason is very simple. Surface water, you can see it. It's observable. Groundwater, it's not. Very simple reason. If you deal with a lake and you make the assumption that there is enough recharge, enough inflow, the estimation of water resources availability is very simple. Actually, when dealing with a lake, your unique concern is not to empty the lake. It's not a problem to identify the volume. You go with a boat over the lake and you measure the water depth, you make a survey, and that's it. You have an estimate of the water volume, and your only concern is how to protect the lake against depletion. So you have to estimate the inflow in some way, but in some cases it's clear that the inflow is large enough. So you don't have to have concern about it. Think, for instance, at the pre-alpine lakes in Italy, Lake of Garda. It's clear that it's a source of water that it's has significant recharge, and you will not get along the year more water from the lake than what flows in. So you are relaxed. Your only concern is to protect it against pollution. So for lakes, it's generally easier. If you have a small lake, it's not so easy. You have also to estimate the inflow. If you go to a river, the problem is apparently simple, but it's not. Because it is very difficult to assess water flow. It's difficult to measure it, and you don't resolve the problem if you measure it once. You have to measure it continuously because it's time varying, it's seasonal. So the problem gets very complicated. And the only way to, not the only way, there are several ways to resolve this problem, and we can split between methods that are based on observing, which means measuring the flow for a long time, and methods that are based on modeling. Okay, let's try to, let just me tell what's written here before I change the slide. And the most relevant challenge, if you decide to use observations to quantify water resources, is lack of data. So, as I said, we can move forward by analyzing data, observations, or by using modeling. The first category of methods analyzing data is also called inductive methods. It means I start from observing the result of a process and I infer about the process. I go back along the process. So you may wonder, but what does it mean, process? Process means, in this case, the physical mechanism that brings water into the river. It's the water cycle in its broad sense. When I go over a river and I measure the flow, what am I doing? I am measuring the result of the water cycle. The water cycle is my process. So I measure the outcome from a process, the result from a process, and I make inference. I try to understand the process by going back. Understanding the process means I want to know how much water this process is delivering. Inductive, because I start from the result and I go back. Okay. And I may decide to give up to try to understand what's going on. I just look at the result, water. I may ignore what's going on in the process. For instance, people in the Middle Age thought that the water flowing into the river was coming from underground. They didn't realize that most of the water was coming from rain. And you may think, but this is very silly, why they didn't realize it? It's very simple, because they didn't have any communication. So when they were in Ferrara, working just on the Po River, they were flooded without any rain, and they couldn't understand that. And so they thought that water was coming from somewhere, not rain. And they assumed that it was coming from the underground. In some cases it happens. In some rivers, of course, it happens, but it's a very rare situation. So they just concentrated on the result. They didn't understand anything of the process, but they were able to estimate water resources availability anyway. And this is because the inductive method just starts from the end of the process, and what happens along the process is not necessary for you. This is called inductive method. It's also called, in our technical terminology, which is an Italian terminology, it's called direct method. Direct because you work directly on the results. This is not international. In international level, it's inductive. Okay, and then you have an alternative. Let's suppose that you don't have any data. So you don't have measures of river flow. So how can I solve my problem then? And let me try to make a sketch here. I try to make it visible by all of you. So basically, let's suppose that I have a river and I want to know in this location here how much water resources is available. And I don't have any observation. So I can use another method, which is looking at the process, understand how it works, and model it. So what is providing water to my location? The water cycle. And how does it work, the water cycle? We all know how it works. So there is some rain, or some snow melt somewhere, rain that falls over what? Over a certain area that contributes to the drainage in my location. So let me identify this area. This is the area where, if it rains, water flows towards my location along the river. This area is called catchment, or basin, usually river basin, or watershed. Synonyms. Watershed is used in the UK, catchment in the US, or the other way around, I don't remember. But nowadays you can treat them as synonyms. Okay, so I identify this area. We will provide a definition for catchment later on, okay, because there is a strict definition of it. But anyway, we identify this area, we measure rainfall or snowmelt, whatever is relevant, and we apply a transformation in order to transform a mathematical transformation to transform rain or river flow depending on the condition of the catchment. This is called, I'm not sure if you can read there, so I just prefer to say it. It's called a model. Precisely, it's a rainfall runoff model. Learn this term, we will talk about it later, so you don't have to be concerned now. But it is a rainfall runoff model. It's an analytical model that starts from rain or snowmelt, whatever is relevant, and estimates river runoff. And you may ask me, but if I don't have enough data in terms of river flow observations. Do I have, is it possible that I have data about rainfall? Answer, yes, because rainfall is easy to measure. River flow, it's not. So in some cases it may happen that you have rainfall data and you don't have river flow data. So a possibility is to apply this rainfall runoff model. You apply a model. It's also called a deductive method. Deductive because you try to learn how the process works. So you start from the process. You learn what are the input data that you require, rainfall rather than snowmelt, and you use a mathematical model that emulates the process to produce the results. So it's the other way around with respect to the inductive methods. It's also called indirect method in Italian. In Italian it's called indirect, of course, but in Italy we use this classification also. And I would say that probably in other countries as well. Usually we say direct methods when we start from data, from observations, and indirect when we start from the process and we try to build a model. And therefore we generate the data instead of observing it. Okay. Now, I started a bit late, so give me, if I may, 10 more minutes from now, okay? May I? Yes, okay. So, first of all, then, we have to check whether we need to assess water resources, and then we check if we have data. So let's start from the identification of the location. Usually it's our customer that tells us, I need water there. In some cases we are allowed to propose a location, and then if we are allowed we have to make some preliminary investigations, but let's assume that the location is either given or predetermined. Usually it's not a big problem to identify the location. I tell you, if we are allowed, usually what we do is to look at the costs of getting water here or there. And costs are related also to accessibility of the place, because you have to build, you have to set up construction works there usually, and therefore you also look at accessibility. So these are purely technical considerations that are not always not strictly related to sustainability. Okay, what is related to sustainability is water resources assessment. So let's suppose that the location is assigned, and then first of all let's assume that the location is a river. So let's start from that, and then we will talk about groundwater later. So the location, the water body is a river, and the location is assigned. Fine. Okay. What do we have to measure? The river flow. So we need to define what is the river flow. And these two definitions that I introduce now are essential, and you have to be able to repeat them. Okay, so first of all, let's define what is a river cross section. Okay, you go over a river where you want to take the water, and the river, of course, is moving. Water is flowing by definition. The river, by definition, is flowing water. Okay, let's concentrate on a given water particle, like I release a drop of red color into the river, and I see this red particle that travels along the river. Let's focus on that red particle. And let's determine at a certain time the velocity vector of that red particle. Okay, so this is a river. let's take this fluid particle of water, and let's determine its velocity vector. Okay, now let's cut the river with a plane that is perpendicular to the velocity vector. Fine. Of course, if you cut the river, you get a section of the river itself, which looks like this. This is the river cross section. And you can understand the meaning. Section because it's a section. Cross because it's perpendicular to the velocity vector. The definition is reported in my webpage. Just look at them. There is one thing that I don't want to go into the details of fluid mechanics. This is something that is already in your background. But I just want to give you a clarification which I think is necessary in order to fully understand why this is a cross section. You may say, Professor, but if instead of this particle I choose this one, and the velocity vector is something like, impossible, but let me try to, something like that. It is completely different, the cross section that I get. Okay, this would be not the case because, but it is an extreme example. Actually, we are talking here about a water flow or water current. A current or flow is defined as the kind of motion of the flow such that each fluid particle approximately follows the same direction. Which means that a situation like that is clearly impossible in a river. You can't get a fluid particle that goes against the current unless you have a vortex or something very singular. But typically in a river, if you drop like a floating body, floating is, floating means that doesn't go, doesn't sink. A floating body, and you go over a bridge and you drop the floating body in the left side or in the middle or the right side, more or less you see that the floating bodies that you develop in different positions, they follow more or less the same direction, which is downstream. Okay? This is because, of course, this is a kind of flow that is very regular. It's different if you take a glass of water and you empty it over the ground where water goes in any direction. In this case, the direction is more or less the same. And this is the definition of a current. A current is that fluid motion where each fluid particle follows more or less the same direction, approximately or more or less. And therefore you are sure that if you get a fluid particle here, or get a fluid particle which is located somewhere else, like here, the velocity vector is more or less traveling along the same direction, and therefore you get the same cross-river section. Actually, when we talk about open channel flow, you may remember that an assumption that we make, which is actually the result of a previous assumption, but we assume that in a cross-river section the velocity vector doesn't change. This is something that I don't ask you at the exam. I just want to make clear to you that when we go over a location in a river, there is a fixed cross-river section passing by there, and the velocity vector in the river cross-section doesn't change. Okay, so it's uniquely defined, the river cross-section, and there is no change of the velocity in the river cross-section. This is an essential definition, and what I want just you to remind is definition of river cross-section, and please remember, please remember that once that you draw a river cross-section, the velocity vector doesn't change in it. If you don't remember this, and you reflect on what you studied, you may not understand what follows. Now let me define water flow in a given river cross-section or cross-river section. The water flow is the volume of water per unit time that passes through the cross-section. Volume of water per unit time. Units. Volume per unit time. Cubic meters per second or liters per second. These are typical units. Okay, let me conclude by giving you a suggestion for a possible, give me a couple of minutes, interactive activity. Couple of minutes. This is sustainability, no, it doesn't work. If you look at my tutorial, there is two suggestions that I want to give you. And okay, first, there is in my tutorial a brief history of urban water supply in antiquity, and I think it is interesting. It's just curiosity, so it's something that I don't ask at the exam, but I think it may be interesting. And there is the link to a scientific paper, which is a review, a PDF, of the history of water supply. So besides reading my lectures, you may want to have a look at the PDF. It's a very easy reading. And you may want to prepare a presentation for next week or 1 week later. If it is a presentation, it's at most 10 minutes. And if I get more than one request, I will manage I will interact with you. My suggestion is, if you want to do that, maybe as soon as you decide, let me know, so I can keep control of what's going on. And if it is a presentation, anyway, let's start with 10 minutes, which means 10 slides. And you may look at the paper or you may look at the web. I think it is interesting and I really would like to see it. If it's a good presentation, then with your permission, I may link it at my web pages. This is the first suggestion. Second suggestion. You can send me also a link of videos related to the lectures. Try to be technical. Your colleagues sending the videos were technical enough. The videos that I received were pertinent and technical. And another suggestion, we talked about water scarcity. There is a very interesting database that is linked in my web pages by FAO. And this database, the second link is just a map of distribution of freshwater uses, and we need to, you see there is this map. If you click on the countries, this is distribution of water uses, and this is the proportion of total water withdrawn for agriculture. And these are the, you see, dark green is 87% of the percentage, 87% is the percentage of total water withdrawal in that country that is used for agriculture. And you see that if you look in the north of Europe, the color is turning to light green, as we said. And if you click on the countries, you get the percentage. Also, there is another link, which is this one, which I think it is interesting. And this is a comprehensive database of FAO. And if you click on a country, here you can select a region or a country. And if you click on a country, like, let's see, for instance, Israel, and you see Go, they give to you statistics on the water uses. And you see that agriculture is consuming about 70% of water. There are other countries, like East of Europe, where the water consumption for agriculture is very reduced. And so you may focus on your own country, which may be Italy or another country, or your own region, and prepare a 5-minute presentation, 5 slides, summarizing what are the water uses for your country. This is another kind of interesting thing that I would like to see, because it would allow me to see how you present and what is your country of origin and what are the conditions in which you typically live. If you want to do like that, again, when you decide, you don't need to make it for the next week, you can do it in 2 weeks. As soon as you decide, please inform me. I will put in the Google Drive what I receive, like Alberto Montanari preparing a presentation on, and so you can see what's going on. As soon as you decide, if you inform me, it's better. Okay, that's it. Subscribe to the mailing list so I can give you visibility to the Google Drive. So we see each other on Monday, and on Tuesday next week, please be prepared to bring your PC if it's possible. Otherwise, speak with me if it's not possible. A PC every 2 persons is fine. Sorry if I went a bit late.